Yeah, I think let's do this. So welcome everyone to another gathering of the community of practice in sustainable concrete hosted by SmartCrete CRC. It's great to have you all here again. This is another opportunity to bring together industry experts, researchers, and the wide concrete ecosystem to discuss ideas, breakthroughs, and best practices around sustainable concrete. Let's not beat around the bush, jump straight in. Today we are talking about power industry byproducts in eco-friendly concrete. And we are tackling some big questions today. Understanding the byproducts of power industry, what they are, how are they produced, is it a waste or gold hiding in the ashes? Their value proposition of these byproducts to be used in concrete, why concrete, is what are the technical speed bumps along the way, so much and so forth. And we are fortunate to have four fantastic speakers lined up, two from industry, Anthony and Steve, and two from academia, three from academia, Patrick, Uma, and Ali, each bringing a wealth of knowledge from both sides of the fence. A few housekeeping rules. This community of practice is being recorded, and for a wider audience, it will be put online later. So bear that in mind. Please keep your mic off while the presenters are presenting. That would be really helpful for the presenters. And we'll hear from each speaker in turn and then open the floor for questions. And if you have a burning question during the talks, feel free to pop it in the chat box and raise your hand and jump in once the presentations wrap up. That being said, we'll go to the first presenter, speaker one, Anthony Callen. Anthony is currently the business development manager at Delta Power and Energy and has over 15 years of experience in the electricity industry. Anthony is committed to sustainability and the principles of the circular economy, consistently seeking ways to enhance environmental performance and resource efficiency of operations with a current focus on coal ash utilization and new product development. And he has a wealth of dad jokes, so I'm really keen to listen from you, Anthony. The floor is yours.
Thanks, Aaron. Can you see that screen? No worries.
Yeah, that's all good, Anthony. Go on.
Good stuff. All right. Well, good afternoon, everyone, or good morning, depending on where you're dialing in from or when you're listening to the video. Yeah, my name's Anthony Callen. I work at Point Power Station down on the New South Wales Central Coast, and I guess my role today is just to set a little bit of a scene of the background to a project that we got involved with SmartCrete and our other industry partners, mainly Daracon. So today I'll just give a quick overview of who Delta is, what our interest in the project was, where we started from, and some of the other issues we worked through along the way.
Anthony, we got you on mute. You there?
I sure am. My slides are blocked. Sorry.
I wasn't the dad joke. I didn't see that dad joke coming.
There we go. All right, we're off and running.
Yep.
Thanks, Aaron. Yeah, so Delta Electricity. So we're like a lot of other coal-fired generators in Australia, just a little bit different in that we own our own coal mine. So we own the Chain Valley Colliery, which is next door to the power station and supplies about 50% of our coal. We're part of a much bigger group owned by a Czech-based family group, the Seven Global Investments Group. In Australia, they owned a couple of other assets, including part of Millmerran Power Station in Callide in Queensland. But Vales Point's their only asset in New South Wales. So our connection with the cement industry, I guess, is through the use of SCM. So as most people will know, that fly ash is one of the byproducts from coal combustion, and we produce a fair bit of it. We recycle about 25% the fly ash into ready mix type cement product, concrete products. But we're always looking for alternative and new technologies to increase utilisation of coal fly ash. This next slide sort of shows where we fit into the grand scheme of things. For those that don't know, that when coal burns in a furnace, that most of the organic material burns and produces the heat, and this which generates the steam, which gets turned into electricity. But the mineral matter that doesn't burn inside the furnace is termed coal ash. And as I mentioned before, we recycle about 25% of that. And then the remainder gets landfilled. There. So you got me there, Aaron?
Yeah, clear now, Anthony.
Yep. Gotcha. So the remainder of the material gets landfilled. And so we're constantly looking for new opportunities and new markets to reuse fly ash rather than landfill it as well. So today's project is the Smart Creek project run through the University of Newcastle, and I'll let Patrick and his group talk a lot more about the technical side of things and where we got to with the project. But I'll just throw up a couple of other technologies that we've been supporting around the reuse of fly ash. So ash, of course, as we mentioned, can get used in all sorts of concrete products, which opens a wide range of materials, including precast materials. And we've been supporting a local group that produce a precast panel that can be used for housing construction. So the U-Panel Group, or Ultimate Housing, based at Summersby here on the Central Coast, and have been using fly ash from Vales Point to generate these precast panels, and have been used in a number of housing projects, including we've built some on-site offices with them here at Vales Point, but also you can see there are a couple of other examples throughout the state. Now, utilising fly ash in cement products is an important area to use a lot of fly ash, but there are sort of standards that require or limit some of the volume of ash that can be included. We've also been working with another group on what they term a very low carbon concrete, which is actually it's a zero cement concrete that they've been working with. So this is an alkali activated cement where they're using high volumes of fly ash and slag from steel making, mixed with some other activators to produce a zero cement concrete, essentially. So the images on the right hand side there are some of the field trials that Patrick and Steve from Daracon will talk through in a little bit more detail. But I thought I'd just set the scene there and with a couple of slides just to show that where we fit into the scene. And I guess the big driver for us for this research project with Smart Creek was looking at alternative technologies and new markets to reuse ash from coal-fired power stations. So, Arun, I might stop sharing there and hand over.
Yeah. Thank you so much, Anthony. That's a fantastic layout for us to build on. And it's great to see. I mean, I was told the other day that we produce about 12 million ash annually, and most of them goes to dams, and trying to do something with it is a great idea. And which is where I would like to bring the second speaker and his team. Professor Patrick Tang is a deputy head of school in architecture and built environment at University of Newcastle. Leads the Circular Economy and Sustainable Construction Research Group, focusing on advanced construction materials and sustainable technologies. He is recognized amongst the world's top 2% scientists, list curated by Elsevier and Stanford University. Since 2019, he has published over 160 papers with 6,000 plus citations, mostly in top-ranked journals. And with over 15 years of experience, he has secured several millions in funding from the ARC, Australian Research Council, CRC, Environmental Trust, and industry and international sources, contributing significantly to sustainable construction and research and innovation. Dr. Uma recently completed his PhD and working as a research assistant with Professor Patrick. Ali is a PhD student who works with SmartGrid CRC on a project focused on developing eco-friendly concrete, with using industrial byproducts. So it's a great team effort, and I'm really interested to listen. So over to you, the team from University of Newcastle.
Thank you, Aaron, for the great introduction, and also thanks to SmartGrid for inviting us to present today. So you can hear me clear, right, Aaron? Okay, thank you.
Yeah,
so okay, so as Aaron said, okay, today we have including myself and also my PhD student Ali and also research assistant Uma. They will also talk about the research and also share their insights during the Q&A section. Next slide, please, Uma. Okay, I would like to begin by acknowledging the traditional custodians of the land on which we meet today, and also pay my respect to the elders, both past, present, and emerging. I also extend this acknowledgement to the Alpaca people of the land in which the University of Newcastle resides and which I work. Next slide, please. So I will start with a very brief overview of the project and also its aims, and then I'll hand over to Uma to talk about, to share more details about the research and also some key findings. Ali, and later on, we also join the discussion during the Q&A section. So just give you a big background about this project. I think most of you'll be aware that coal ash is actually one of the Australia's biggest waste problem, accounting for nearly 20% of nation's total waste. And at the moment, each year, around 12 million tons of ash are produced by coal-fired power stations. Disposal of this ash is becoming an increasing environmental concern. But the good news is that reusing 1 ton of ash, we can prevent approximately 0.87 tons of CO2 emissions. While there is a modest market for fire ash as cement replacement, furnace bottom ash is, relatively less commonly used, and with large quantities of FBA end up in landfills or ash ponds. Next slide, please. So this project, we focus on exploring innovative ways in order to use FBA in concrete. We try to reduce environmental impact and also support Australia's transition toward sustainable waste management practices. It's an industry-driven research project. We try to develop practical, impactful solutions to solve the ash problem. And this project is funded by and also supported by SmartGrid and industry partners, including Delta Electricity, Daracon, Concord, Ash Development Association of Australia, and Transport for New South Wales. This project also received some support from the researchers at RMIT. So we are Newcastle University. We are the lead of this project, and that is the background of the project. Now I hand over to Uma. Thank you.
Thank you, Professor. So today we will be talking about the specifically with the furnace bottom ash. So first of all, what is furnace bottom ash? From coal combustion electricity power generation, we have a lot of ash production, and out of which is one of which is furnace bottom ash. So it's the collection is from the major portion of the furnace bottom ash sometimes end up in ash ponds for reclamation, or sometimes a few of the quantity can be reused for different purposes like embankment fills or like fine aggregates. So the production of in Australia is around 10 to 20%, which is around 1.3 to 2.6 million tons annually. Just talking about the furnace bottom ash. And in composition, it's chemically similar to fly ash, but with the larger particles. So when we compare it with the cement and other cementitious products, so it's a bit slightly coarser than those cementitious products. So that's why we have to like treat it doing some pre-treatment. Then we can use it as SCM or as other fine aggregates. So the benefits of reusing the furnace bottom ash is, of course, the environmental sustainability. When we are using furnace bottom ash, specifically, we use it as a partial replacement of fine aggregates in concrete, and also we are developing and researching to use it as a SCM in concrete. So we can replace cement as well as we can replace natural sand. So when we are using we are replacing the natural sands, of course, we are like using less virgin resources, and we will promote the circular economy initiatives by reclaiming furnace bottom ash from ash ponds, and then we can use it in concrete for long-term utilization. And then decarbonization and climate goals. Of course, when we are replacing cement, so we are replacing or lowering the carbon dioxide emission from the concrete production, and it will, of course, reducing the footprints of carbon from construction materials and from infrastructure projects. And it also has a benefit of like it is aligning with the National Waste Policy Action Plan, in which we have like resource recovery options and then reduction in waste generation. So if we are using the furnace bottom ash in concrete and we are not like landfilling it and not making more ponds of it, so it means we are like reducing the waste generation, and then it is a recycled content as well. So these three major points are from National Waste Policy Action Plan. Then we have performance advantages. We can use furnace bottom ash in multiple things like road-based embankment fields, and it is also suitable for concrete. In concrete, we have major focus to replace it with, as said, fine aggregates, and also we are working on to replace it with cement. Then the economic efficiency, of course, when we are using the recycled products and reusing it, so the cost is significantly lower compared to that virgin or natural aggregates or the products which are available in the market, and it also like reduces the energy usage which is utilized during the extraction of the natural aggregates and also for the production of the cement. And the last one is the resource optimization when we are using the coal combustion byproducts. So of course we are like reducing the extraction of natural materials and also the reduction in the carbon footprints from the cement industry. So first we have published an article. It's a review article. It has been published in a top-notch international journal. So in this article, we have like summarized all major of the portion about the furnace bottom ash, in which we have focused on characterization, then the practical application or the different research backgrounds which have been implemented to use the furnace bottom ash in concrete or in some other applications. This paper also focuses on the United Nations Sustainable Goals, specifically 9, 12, and 13. So in this, we have put up summarized the whole of the thing into a compressive strength photo, which you can see on your screen. Because compressive strength is the major, or you can say the most important parameter which we use to determine the characteristics of concrete. So in this slide, you can see although the replacement level goes up to 45%, but the strength goes significantly reduced if we use furnace bottom ash as SCM or sometimes with fine aggregates, but up to a replacement of 5 to 10%. So this the strength is not that much reduced compared to the control concrete. So, but how we are like using the furnace potash, and what are the major parameters? First of all is the particle size. As said, it is like slightly coarser than fly ash and normal supplementary cementitious materials. So that's why it is feasible to use it as fine aggregate as well. It has high porosity, high water absorption, and the shape and surface area is like slightly higher compared to the natural sands. And but it meets the compliance of AS 27581, in which we can like we have compared the characteristics of furnace bottom ash with the aggregates which can be used in concrete and mortar, and it lies within those ranges. And for FPA as a SCM, we have to treat it with the different methods. Then we can use it as SCM. As said, it is slightly coarser and it has low pozzolanic activity. So different methods have been opted in research, like heat curing, grinding, activation agents, or blending with other SCMs. What we have adopted blending with other SCMs, because heat curing, again, you will not get much benefit if you are doing it heat curing, and you can't do the heat curing at the site specifically for in situ production or in situ usage of concrete. Like heat curing is very difficult to apply. And then preferred method is, which we have opted, is the co-grinding or blending with SCMs for lower cost and expertise. In our case, we have used ground granulated blast furnace slag, and we have co-grinded the FPA furnace bottom ash with the ground granulated blast furnace slag. And then we replaced cement with that blend. In addition to that, we have replaced natural sand with furnace bottom ash. So it complies. We're working on the compliance with the transport of New South Wales specifications, specifically R53 and R83. This is the particle size distribution results of the furnace bottom ash obtained from a couple of sources, and from one source we have done like couple of analysis. We have a chemical composition and also the particle size distribution. So we can see that furnace bottom ash lies perfectly within the Australian standard limits of coarser and finer aggregates. So we can easily, as per standards, we can easily use it as fine aggregates. These are some key findings from our research, which we have done here at University of Newcastle. So we have slump values. Here I am like showing the 5 mixes from other major mixes we have done here in University of Newcastle. So the first one is CR0, which means the control concrete without FPA and without any other addition or replacement. And CR25, it is controlled concrete, but we have replaced 25% of natural sand with furnace bottom ash. And then the other 3 mixes are CGF10, CGF20, and CGF30, which is co-grinding of furnace bottom ash with slag. So we have replaced this 10% cement with grinded FPA and 20% or 30%. So if you have any question about the mix ideal, let me know. So we have slump value first of all. So the slump of the furnace bottom ash concrete mixes is slightly higher. You can see here, but why it is higher? As the water absorption of the furnace bottom ash is higher, so we have used additional amount of super plasticizer to make it more workable. Otherwise, if when we did the trial testing or like preliminary testing, but we have found that lower or the similar amount of super plasticizer as control concrete, we can have a harsh mix, which is like very difficult to work on it and very difficult to place. So what we found that if we can increase the amount of super plasticizer and slightly increase the amount of water absorption, water in the concrete mix to account for the water absorption of furnace bottom ash, so we can have a better mix which is workable and can be easily placed. So that's why the slump of the initial slump of these FPA concrete mixes is slightly higher compared to control concrete. Then if we come with on the density, We have measured the density at 28 days. It is hardened form of density. So we can see that as per density, the furnace bottom ash mixes lies within the range of the normal concrete densities. And there is not much difference between controlled concrete and with the mixes with furnace bottom ash. And you can see the most preferable one is the CGF10, in which we have replaced 10% of cement with furnace bottom ash. Then we have splitting tensile strength test, in which we have compared all of these 5 mixes, and we have performed the test at 28 days. And in this test also, you can see that 10% of usage of furnace bottom ash is provided the slightly higher splitting tensile strength compared to the other mixes, and the strength is comparable to the controlled concrete. So in terms of technicality, we can see that we don't have any much difference between controlled concrete and the concrete, with using furnace bottom ash as 25% of natural sand replacement and 10% of cement replacement. Then we have water absorption. Although the initial water absorption of furnace bottom ash as a raw material is high, but when we have utilized it concrete, so the results we have obtained is promising that for 10% of replacement mixture, we have slightly lower water absorption compared to other concrete mixes. Then here we have summarized the compressive strength and some other tests which we have conducted here. Like for workability, we have also done the slump retention test and air content test. And for strength, we have done flexural time models of elasticity test as well. And also we have focus on durability tests, especially on shrinkage, abrasion, and carbonation resistance. Also chemical resistance against acid and alkaline solutions. And we have also done the microstructure analysis and life cycle assessment. But here, as of time, we are like showing the key findings or just the major findings. So here we have, I am like showing the results of compressive strength up to 90 days. We have conducted the test, and you can see that the 10% replacement mixture, it produces like promising results when we have like compared it with the control concrete. Then we have done the life cycle assessment. For life cycle assessment, we have set the boundary conditions from collecting the waste materials and to produce the concrete at concrete patching plants. So we have used FBS sand replacement and also FBS as supplementary cementitious material. So again, we have 5 mixtures here. We have a significant reduction in carbon dioxide emission. The emission for the control or the mix with 25% as FPA as fine aggregate has around 400 kilogram per kilogram of CO2 per meter cube. And when we are utilizing FPA as SCM, so around 36% of reduction in carbon emission was observed. Similarly, for the cost, of course, when we are replacing the natural aggregates and also replacing these cement with the furnace bottom ash, so the cost was also reduced for all of these 3 mixes. And this is a picture from our industrial application. Thanks to Anthony from Delta Smart Grid CRC and Daracon. From all of this team, it is possible to have the industrial application of this FPA concrete mix. So here we have 3 sections of the footpath in which we have utilized for concrete or normal concrete for one section and FPA concrete for the other one. And we have up till now we have good results for not any significant change in the performance of FPA concrete compared to the control concrete. These are some challenges and solutions which is you can say for the furnace bottom ash to utilize on the mass scale. We have some technical challenges in which the major one is the standardization of the furnace bottom ash. Like if you are using for obtaining furnace bottom ash from different sources, there might be slight change in the properties and chemical composition. Sometimes there is slight change in physical properties as well. Like in some cases we have a like coarser particles, and in some cases we have a slightly more finer particles. And then there are some regulatory and standard challenges, like in terms of handling of the furnace bottom ash, storing of the furnace bottom ash, and as said, if utilizing furnace bottom ash as SCM, we have to grind it. So, of course, we will grind it well beforehand to utilize it in concrete. So we have to consider about the handling or storage of those ground furnace bottom ash. And then there are some economic challenges, and those economic challenges is specifically related to the pre-treatment of furnace bottom ash to be utilized as both SCM and as fine aggregates. And then there are some logistic challenges because we have a few number of coal power stations around the state or around the country. So to like transport those furnace bottom ash to the desired locations, we have some like limitations, or sometimes we have some supply chain issues. For overall view of the project with the Smart Grid and other industrial partners, we are up till you can say at the end of the project. So we are in current stage, we are like developing some guidelines so that the normal or the public can use or utilize or can get the overview or can get the guidelines for the use of furnace bottom ash in concrete and in construction industry. Thank you. That's all from my side. Thank you.
Thank you, Patrick and Uma. A great presentation. I think one of the common misconception in our industry is that as soon as the material is sustainable, it's going to be super costly and it's not cheap. But I think this initial research at least show that it's not only sustainable, it's also 30 to 35% cheaper, which is great thing to look at. And another challenge is to scale up and produce on a large scale, and that's where we go with our fourth speaker. But before I introduce him, anyone have a burning question, feel free to pop it in the chat, and we will take the questions after the presentation. So the last speaker, Steve Butterfield from Daracon, Steve has over 30 years of experience in the construction industry, working both in large and small contractors. He has held over various concrete quarry and project roles in concrete production, major projects, and technical management. He has had a long involvement with Daracon Group and others, including RFK Engineering Services and BHP. He spent 10 years involvement in the BHP Jansen Canada twin shafts project in weather conditions ranging from -40 to 40 degrees. And the Woodsmith project for twin shaft construction in Whitby, UK, both specializing in super workable concrete. This is at SWC concrete. Current projects he is also involved in include BHP Prominent Hill, South Australia, is a 1.3 kilometer Waira shaft project, and K92 gold mine construction project in Papua New Guinea. So he's been around the world, and it's great to have you here, Steve. So to you.
Thanks, Arun. You hear that?
Yeah, clear. Yeah, but
I'm sharing my screen here. Is that sharing?
It's the other slide, Steve. So maybe go to slideshow and start from beginning. The slideshow. At the top, like on the home. The slideshow is a few tabs on the right.
Okay, how's that?
Yeah, that might work. Yeah.
Okay, thanks for that introduction, Arun. I'm just coming at this from a point of view from Daracon. Just before we start, I'd just like to run through a little bit about the Daracon group and also talk about some of the other work they're currently doing with their fly ash business. The Daracon Group was established in 1983 and it's one of the largest family-owned construction businesses in New South Wales with over 850 employees. The Daracon Group is a collective of businesses. You can see there on the left, it's pretty substantial, committing to delivering superior civil construction services across both the public and private sectors with over 4 decades of experience. So they have civil engineering, concrete, quarries, empire, infrastructure, all the way down to polywelding and landscaping. Demand for construction materials through Daracon can be more than 3 million tonnes per annum through quarries, concrete and the fly ash businesses. In the past several years, Daracon has proposed the use of pond ash from Mirari in various projects. They have spent a lot of time on research and development with that. Part of their business is obviously their bulk fly ash with Daracon. They do underground grouting and mine backfill. For the past 5 years alone, they've averaged the reuse of approximately 200,000 tonnes per annum of ash. Residential and commercial developments in Newcastle forecast for a long future of this type of work. 2 recent projects have seen a projected use of approximately 250,000 tonnes of material in the coming year alone. They're also working on heavily bound material, modified rose-based materials, investigating potential use of pond ash and small volumes of cement for setting currently. The initial trials were undertaken late last year with various viable sources of materials. Trials included different sources of ash and locally available fluids to gain optimal mixes across different strength characteristics. So this obviously includes select, modified, lightly bound, and heavily bound material. BFG Daracon business also is obviously established at Orari. Production of a current plant is approximately 60 tonne an hour. It has an ability to classify around the 500,000 tonne of grade 1 fly ash product, and it has 1,000 tonne of on-site storage capacity currently. They're also at the moment investigating several different options for plant design and development, with the final concept formulated once results of the investigation are available, as the design will be tailored pending characteristics of the fly ash ponded materials. With a high-end cyclone air system being installed within the coming months, BFG Daracon will be positioned and equipped to dial in any blend that a client may require. And BFG Group also has initial trials for bulk grout undertaken in late 2024 with various source materials again. They've had successful test results in a variation of strength parameters up to 60 MPa. They've had success with up to 100% cement replacement mixes being designed. Obviously, the target markets would be within the residential, commercial, and civil sectors. The Daracon business, which is the concrete branch of Daracon, it also currently has a range of 50% plus high-range fly ash concrete mixes, which we've used successfully previously, as well as supplying with the bulk fly ash group CLSM 90% fly ash and high-strength grout for mine fill and mine subsidence. We also specialise in a lot of super workable and high workable concrete. We've got developments of near 70% SCM blended concrete mixing, and we're looking to utilise the waste concrete aggregates with the Daracon Butterfield recycling facility, which is shortly to come online. So there'll be a lot of work involved in that. The Daracon plant has also conducted trials with unique SEM, as Anthony discussed, and it's achieved pretty good results, and it's a low carbon alternative from the material class known as inorganic polymers, and it can initiate total GP cement replacement also. Daracon have also, apart from some smart creek trials, we've also done work just within the group as well, looking at what we can do and what mixes we can come up with. These ones were done approximately 22 months ago. And these first 4 trials were basically just, we had a control 25 MPa. This was done in conjunction with the construction arm of Daracon. So we had the concrete, we set out an area with Daracon provided for us and set up 3 test slabs, which you'll see shortly. The first mix is basically just a regular tri blend, which most guys here in the technical would be familiar with. So it was just a tri-blend of basically fly ash cement and slag. And the second one was a recycled coarse aggregate was added to that same tri-blend as the next two. And then the third one, we incorporated the same tri-blend of slag, cement, fly ash with a recycled concrete, but also had 100% fine sand replacement with the furnace bottom ash as a fine aggregate. You can see the area there. So we've got the eco, we've got the second one, which is with the recycled ag, and the third one is the trifecta of the tri-blend with the furnace bottom ash as sand replacement plus the recycled aggregate. You can see on the right hand side there, obviously trial 3 had some substantial cracking early on, which was predicted. That was a really hot day, and we provided no curing for that at all. We're trying to sort of simulate what the residential market is, which I think most guys on listening to this will know it's pretty rubbish with when it comes to curing. So we just wanted to try and match that, see what happened. Obviously, with that amount of slag and that amount of fines in there, obviously water demand was really high. The second lot of site trials we done was in conjunction with Leighton Quarry City Council. This is a pathway at Quarry Fields. We didn't provide a control mix there. The control mix you can see on that chart there is just for reference. So we only provided a tri-blend eco blend on this, which was basically a 50-50 cement slag blend, but we used a recycled aggregate and some of the furnace bottom ash fine aggregate as well in that. That went particularly well. The path is still looking really good to this day. Obviously, the product, as we're aware, with slag mixes, but then when you add the recycled aggregate, it has a very high water demand. So you can see the results there on the right compared with the control, very only 3 MPa at 3 days compared to 13 with regular concrete. And as we know, the growth is obviously a lot better in slag concrete than what it is regular concrete. So at 28 days, it's more than passed. Site trials 3 are obviously the ones that have been discussed here. That's usually the Vales point material. Again, here we had the control mix, which the guys have gone through, which is basically a standard 25 MPa 100 slump. That was in one part of the footpath, and the other part of the footpath had the tri-blend of GP, slag, and ground, also containing ground bottom, furnace bottom ash as a cement replacement, and we also had the furnace bottom ash as a sand replacement in that mix also. As per the presentation, but as well, you see the product worked particularly well, considering that was a 45-minute delivery time as well. So the load 2 obviously lost a bit of slump, so obviously has a larger water demand. There's a bit of a colour difference. But as of the next day, when I went down there was no initial cracking, which is a really good sign. Now, the conclusions from a lot of this is concrete is obviously a robust material and can only be made with materials. I know from my personal experience, did a lot of work in PNG with such as select fill, crushed coral, and all sorts of stuff we can put in concrete. The mixes presented here have the ability to be produced and placed successfully, not a problem at all. However, the production using these materials needs a high level of quality control and good site practices. The delivery and storage of the ground furnace bottom ash and the furnace bottom ash as a fine aggregate, the batch plants requires further progression for bulk deliveries in future if the market uptake is large. Obviously, the storage of the fly ash in as a fine aggregate, it's hard to go through bins and tends to want to jam in bins, so the conditioning of that would be an issue. And that goes equally as well as anyone's worked with recycled aggregates knows how important it is that those things are absolutely soaked in water. They just have such a large absorption, and anything any concrete leaving batch plants will come back by half in slump if it's got any sort of delivery distance. The performance specifications rather than prescription. Now this is the big one. It has to be promoted by specifiers and designers. Concrete suppliers shouldn't do all the heavy lifting on this. Daracon, we've been really fortunate because we've got the Daracon construction arm. And so we've had a joint effort in a lot of the work we've done, and those guys do everything to an infrastructure standard, including placing and the like. But a lot of this would be aimed at residential, and those guys tend to, 80% of that is, there's no curing, there's no vibration, and there's not a lot of the good practices. So it's really up to us, like the specifiers. We really have to sort of push the specifiers to, if we want to use this stuff, it's just a matter of the guys on site getting used to what are the good practices with this, and if you're going to get more cracks out of this than you are with regular concrete, that's just got to be expected. But if it's for the greater good, that's what we have to design specifications around that. Going forward, Daracon Group will continue to alternate concrete to help reduce environmental impact and provide clients with solutions for their project needs. Reduction in CO2 currently in regular high volumes for 25 MPa grade concrete in the residential market. The greener concrete, I think, is the market to target. Obviously, a lot of this stuff, and guys would know, if it's 40 MPa plus, it makes it extremely hard. Future use of bottom ash, ground and fine recycled aggregates from Daracon recycling Bud-eye, enabling repurpose of waste products with a focus on removal and reduction of waste pond ash materials, further promoting a circular economy is obviously the main aim here with what we're doing, and hopefully we're looking at that in the future. Thanks very much for that.
Thank you, Steve. And it's a great presentation. It's great to see the amount of work that's going into it in scaling up, and our chat sections up and running, which is great to see for us. Jared Wilson I think there is a conversation going on in chat, so I'll probably quickly read it for everyone's benefit. So Jared asked, does the ground bottom ash comply with AS 3582.4? To which Patrick answered, the short answer is yes. The ground FBA complies with 3582.4. In fact, we compare its performance against AS 3582.1 for fly ash, which is more stringent than 0.4. And of course, Jared pointed out LOI is quite high, loss on ignition. Does this impact admixture interaction, air and drainers, and so on? To which Patrick answered, we haven't studied the interactions with air and drainers yet. Could be a focus for future research. Jared, do you want to expand on it more? If you are.
We find with fly ash with a high LOI, it's hard to entrain air.
Yeah, I think my thinking here is we don't use much air trainers because we don't have freeze thaw in here, do we? Except
not so much in New Zealand either, but it's useful for workability and it adds a better finish under the trail. So in New Zealand, typically up to 25 MPa, all concrete is air entrained, regardless of whether it's freeze thaw or not.
I think
it's typically similar over here for just our regular 25 MPa and below in winter months as well, just to assist with a bit of stopping the bleed.
Yeah, I think that will form part of the future research at this point, I think, in Patrick's team. And Olivia had a question. Olivia, you put your hands up. Do you want to jump in?
Yeah, sorry, I don't mind asking my questions. I was just going to add a comment in regards to the LOI. I think it would be good just to add that to the research, because I think especially in New South Wales, when you have the LOI requirements, specifically when you look at your Aurora and fly ash, I think it would be good to add to the research in regards to how it can impact air entrainment when it comes to using pond ash. But my question to you, Steve, thank you so much for a really good presentation. Did you have any issues with chloride content? Did you have really high chloride content when you were making your mixes? And I guess, how did you deal with that?
We have cylinders that we didn't end up getting tested for chlorides. Sorry, Olivia. Patrick, did you do chloride and sulfate testing on the concrete?
Yeah, I mean, regarding the high chloride content, we did study the amount of chloride content present in the bottom ash, and we found that it's high, but still within the standard requirements. And we also brought this issue, I mean, back to delta electricity. So whether what is the typical process they store or handle the pond ash. So I think maybe Anthony, you can provide more information, and also I think what we can do in future. Chloride content may be a concern. I mean, that may lead to steel corrosion, and perhaps one of the treatments that we can do may be how we can minimize the chloride content in those pond ash before we use. Anthony, you have something you want to add?
Yeah, thanks, Patrick. It's a good question, Olivia, and it's certainly an issue that's on the radar, particularly when looking at the large volumes of pond ash that is available for the future. The international experience of digging up landfill ash has been quite positive, but a lot of the repositories overseas have been freshwater based, whereas in New South Wales in particular, it's a saltwater storage medium. So it's something we're certainly working through. I think the Hallett Group in South Australia are probably a step ahead of everyone in developing or developing a process themselves. So we're all watching very closely on those sorts of projects, but aware that it's probably an Australian specific issue to work through, and certainly conscious of it.
Yeah, I can tell you, Olivia, I know Daracon did doing a lot of work with that, obviously looking ahead with a processing plant, and that'll be a lot to do. So that's going to, it's critical that the fresh water flushes the chlorides out of there to a level that's acceptable for concrete use.
I mean, of what I've heard, from Port Augusta fly ash, Hallett Group in South Australia is trying to work with the pond ash from Port Augusta power plant, and they are going through a lot of chloride issues, and their processing has multiple washers to reduce the chloride and so on. But then Gerard has a really interesting questions on heavy metals, because this is a very Victorian problem from where I am based, and I would like to know how do you address the heavy metals in the ash during processing?
So all the ash in New South Wales has to meet a specification under the Resource Recovery Order and Exemption framework. So that's how we manage ash and trace metals at the moment. I guess we're working through a little bit on sort of profiling what's in stored ash, and whether that has become mobile or changed over time. So it's still that's an area of pretty close research as well.
That's really good, Anthony. Thank you. And maybe I have a couple of questions to anyone can take it. Like, what are the applications do we foresee for this concrete? That do we see this concrete as replacing the concrete that we produced in large scale, or this eco-friendly concrete is going to be a portion of? Is like for specific application oriented?
Oh, I think, in my opinion, it can be very large scale, and depending what the residential market wants and what the specifiers in the Australian standards call for. There obviously has to be changes in the Australian standards for pathways, residential house slabs, those sorts of things, but there's absolutely no reason that this can't be promoted into those things. I mean, there's obviously low-hanging fruit with not only this sort of concrete, but that's with the Australian standard at 28 days. If you wanted to make residential construction at 56 days, acceptance strength into 28 days, well, you just do rough sums. I think there's 29 million cubes produced a year, so even half of that, if it's only residential, 50%, that's 14.5 million. So you'd be looking at a 20 kilo reduction in cement for 56 days strength instead of 28 days strength. That's sort of minimum. So you're going to have those 290,000 tonnes straight away stripped of cement and CO2 per annum just by. So the residential market is key, apart from obviously grout and piling mixes and things like that. But I think high strength and ground slab applications for the guys that are placing it, it's unless there's a real joint team effort, it's really hard for the guys that, you're just constantly fighting on projects when this is just for regular slag mixes without other applications. There's always a lot of problems, so you have to feel for the guys that are placing concrete. You have to work closely with those guys because they're usually the last ones in the loop, and so they see it. It ticks a heap of boxes for designers and concrete suppliers, and a lot of guys get it up the gate. But when it gets to site, there's a lot of issues on major infrastructure projects.
Oh man, I work for Precast, mate. I am even below the last. I'm one after the last person in the line in terms of pushing the innovation forward. I know for sure we are all moving the boulder uphill, and but in terms of regulatory challenges and standard compliance issues, what kind of work has been done so far, and who do you think should push this forward in your opinion? Anyone can take the question.
Well, I'll jump in first, Aaron. I guess, as far as standards are important for many reasons, from a design perspective and to give consumers confidence in materials. I guess internationally, other jurisdictions have taken some different pathways in that the US developed their non-prescriptive standards, so a performance-based standard that's available. It's something we don't have in Australia and would be worth considering. And I know that topic comes up in a lot of discussions. So it'd be interesting to hear from the other group about is that driven by research, or is that how do we support perhaps moving down that road?
Yeah, I think I'd like to get Patrick's opinion on this as well, because we do a lot of research. I come from an academic background before I moved into the industry, and I've done my research, and we push and develop a lot of new things. But then to get into the industry, there's always a barrier in terms of standards and what can be done and what cannot be done. How do you think, Patrick, that this can be scaled up, and what are the opportunities here?
Yeah, thank you. I think, Aaron, this is actually a big question for everyone about the standard and compliance.
I put you on the spot.
And when Umas when he present one of the slides is about the challenges and solutions. He also talked about the standard compliance, and I think something that we need to work on, maybe to get more results, data, and which can provide more confidence in terms of the quality of the materials. Yes, I think that's something we not only university can work. We need a more collaborative approach to work together. To develop more guidelines, handbook, etc. So one of the deliverables actually out from our project is we try to develop a handbook about how to use FBA in order to tick all the boxes in terms of the treatments used as SEM or sand replacement. So we try to come up with some guide, but education is also very important. So even though we have a new product, we tick most of the technical performance boxes, but the industry or the community, they still they don't have that cultural shift using those waste material, that is still very difficult. Perhaps maybe a council, local government, or state government can they can help to push using those materials. Otherwise, it's so difficult for only, university. So we have done all the hard work, okay, to say that these materials take most of the bosses, they are safe to use. But in the end, it's always so hard to put that into the market.
I think this is where Smart Grid is doing a great job in terms of bringing the industry and academia together and to find solutions that can directly be applied in the industry, and that's great. I think considering the time we are almost over time, so we'll leave the questions there. Thank you to all the presenters for speaking and sharing your thoughts around this evolving industry. It's a great learning curve, and all the best for the rest of your research and adapting it to the construction industry. You are pushing against the weight of regulations and capital, so I know the feeling. Sometimes feel like pushing a boulder uphill. For any follow-up questions or collaborations, please reach out to Smart Grid CRC. We'll make sure your messages get through to the right people, and you'll hear back. And this is from us today. Thank you for being a great community, and enjoy the rest of the day. Thank you.